So good morning. So in our last class we have discussed about the basics of IIR filter design, right? So we discussed about what is the importance of placing the pole within the unit circle, and what happens if we place the pole on the unit circle or outside the unit circle. Okay, so and how it affects the amplitude response, and we have seen the example with the seen what happens with the help of a simple example, one pole filter, right? Now from today onwards we will be looking into the IIR filter designing numericals. So we have this first one, impulse invariance methods. The second one is the bilinear transform method. Third is the frequency transformation method, and last one is the approximation of derivative methods. So in today's class we will be covering the first one, impulse invariance method. In the next class we will be covering the bilinear transform method, and in the third and the fourth topics it will be covered in the third class. Okay, those are bit short numericals. In fact, when we talk about this impulse invariance method, it is one of the most simplest method. So if you see what happens in the impulse invariance method is that a pole 1 by s minus p1, it is being replaced with 1 by 1 minus e to the power pit z inverse. Okay, e pit z inverse. What is pi? Pi is the location of the pole. Okay, pi is the location of the pole, and capital T, it is the sampling period, and it is inversely related to the sampling frequency, right? Now you just have to do this thing. So wherever you see 1 by s minus pi, you just transform it to this one. Okay, so from here if we look into the positioning of the pole, the positioning of the pole is at s equals to pi. Okay, and in the digital domain, what we have in the digital domain, we find out the location in terms of the z. So we, by solving it, by multiplying with z divided by z, we get z minus e to the power pi t. Okay, so when you equate it to 0, you get z equals to e to the power pi t. So s equals to pi, it is being transformed to z equals to e to the power pi t. At that location our pole is being placed. Okay. However, we know that s is equal to sigma plus j omega. Okay, sigma plus j omega. Now over here, if you see, the omega has been represented in this ohm form, right? So previously I have told this omega, it is related to analog frequency, and the omega which is in the form of W, it is basically related to the digital frequency. Okay, so when we are talking about this frequency in the S plane, we are basically talking about the analog frequency. Hence S is equal to sigma plus j omega, and herein we basically get that z is equal to e to the power st. Why? This pi location is basically the location in the S plane, right? So we just put z equals to e to the power st. Okay, now this s value, it is put over here, and then we get this equation, e to the power sigma 1 t multiplied by e to the power j omega 1 t. Okay, so what is the modulus? This is the modulus factor, which is also basically the radius of the unit circle if sigma is equal to 0, and e to the power j omega t, it helps us in analyzing the phase of the filter. So phase of that filter would be sigma 1 t, whereas modulus of z, it would be equal to e to the power sigma t. Okay. In general, when sigma is less than 0, in the S plane we are in the left hand side plane. So in the Z plane, where we would be within the unit circle. Basically, you just remember the mapping of the this S plane. This was sigma and j omega. This is the S plane. Okay, and then we have the Z plane. Okay, so when sigma is less than 0, if you put sigma less than 0, it will be less than 1. So that means this would be mapped within the unit circle. Okay, so when sigma is equal to 0, this modulus of Z, it would become 1. It is nothing but this frequency axis, it is being mapped onto the unit circle. And lastly, when sigma is greater than 0, so it comes outside the unit circle. So if you see, whatever the criteria we have discussed at the initiation of the filter designing methods, all the rules are fitting over here. Okay, we are not deviating. But from where we started with the location of the pole in the analog domain or the continuous time domain. Okay, and just by applying a single transformation, we were able to get into the digital domain. Okay, so what does this mean? This means that if you have a stable analog filter which is working totally fine, because when you are talking about designing an analog filter, you have to design the analog filter itself, right? So when you have designed any analog filter and it is working perfectly, so you can, and it is solving your purpose basically. Okay, whatever you want to whatever you are trying to solve, it is able to solve it properly. Then it is possible to transform that same filter into the digital filter with same or similar characteristics. Okay, with similar characteristics, right? So this is the thing, and you see it is very simple. Now when it is very simple, so are there any disadvantages? Okay, before going into that, now let us look into the other aspect, how the frequencies are related. So when we understand how the frequencies, that means the analog frequency which is associated with the analog filter and the digital frequency which is associated with the digital filter after you will transform, how they are related, then you will be able to appreciate what are the disadvantages this method will bring into while you are trying to design the filter by the impulse invariant method. Okay, so as I told you, when you are having a stable analog filter, you can use the specification of the stable analog filter to design a stable digital filter using this method. Okay, now just now we have seen that Z is equal to e to the power st, right? However, we also know Z is equal to R e to the power j omega, right? From where it comes? You have the unit circle, this is the radius, and you are on this thing, so this radius is the modulus and e to the power j omega, and this is omega, and this is real Z, imaginary Z, right? Now both the Z's, they are same, both the z's are same, so we can equate both of this. So when we equate both of this, we get r into e to the power j omega equal to e to the power st, but again e to the power st is equal to nothing but sigma plus j omega t, right? So that's what it has been written. Now from here, if you see, r equals to e to the power sigma t and omega t, digital frequency equals to omega t, which is the analog frequency multiplied by capital T, the time period of the sampling. Okay. Now by rearranging, we get omega equals to omega by capital T. Analog frequency equals to digital frequency divided by capital T. So from here, what we get? We get analog frequency is directly proportional to the digital frequency. Okay. Theoretically it looks awesome. You don't have to do anything, right? So are there any problem? Yes, there is a problem. When we talk about analog frequency, it varies from minus infinity to infinity. Right? But our digital frequency 0 to 2 pi. So now can you understand what is the problem? So the problem is that there would be many to one mapping. So how that is happening? Before I go into that, so let us undertake this. Theoretically, we will go from in the digital plane 0 frequency to 2 pi frequency, and again when you go higher than 2 pi frequency, this again you will be moving on to the same points because it is circular in nature. So similarly, if you go into the negative domain also, you will be just moving on to the unit circle itself. So say for example, at pi by 2, you will be having several frequencies which are being mapped onto the pi by 2 point, right? Similarly, at pi you will be having multiple frequencies. So that phenomena, it is called many to one mapping. And when you have many to one mapping, there is basically, we call it overlapping of the frequencies, which is nothing but the aliasing. Okay. Now here we are talking about 0 to 2 pi. Wonderful. But can we use all the frequency range from 0 to 2 pi? No. We are only restricted in 0 to pi. Because in pi we are having the sampling frequency. FM, maximum frequency which is being carried in the signal, and at 2 pi we are basically having the FS, sampling frequency. Okay, so what can you say? So this impulse invariance method, it beautifully works when we have a low pass filter and if you want to emulate that low pass filter. Okay, because if you look from here 0 to infinity, when you are going, you are basically restricting it somewhere over here, FM. Are you getting my point? Somewhere you are just restricting itself, and this is the restriction because of the frequency mapping. So even though at the first go it looks like it's a wonderful thing that analog frequency is directly proportional to the digital frequency, so we can put whatever in the same frequency component we will get, but due to this phenomena of many to one mapping, which incorporates aliasing into the signal. Due to that reason, we will not be able to do the thing. Okay, and that is a problem. Okay, now to solve this problem, what you have to do, we have to band limit the frequency component. We have to band limit the frequency component of the signal, so that our Fs, this Fm, it is within that range. Basically what we do, after band limiting, we also what is the maximum frequency you want to analyze, that you can set, and also the sampling frequency you can set. By changing these two parameters, you can restrict all the frequency components to be lying in the region of 0 to pi. Okay, then this is the simplest form, and from this form the other transform methods have also been derived. We need not to go into the derivation of those, but you have to remember these equations. Okay, so there is nothing you can do. There are only 3 equations, you have to memorize it. Okay, one important thing, when you are using this cos function and all these things, please be reminded that your calculator, it should be in the radians. Okay, it should be radians. Many students, they do mistake. Previously also I have told, whenever you are doing this kind of this numericals in filter designing, make sure your calculator is in the radian mode, otherwise whatever the results you will be getting, it will be incorrect. Okay, so next is, let us take an example and try to solve this. Hs equals to 1 by s square plus 5s plus 6. So it is basically an all pole filter. So by partial fraction, what you can do, you can break it down. So by the partial fraction method, we can say Hs equals to a by s plus 2 plus b by s plus 3. Okay, then after solving it to the partial fraction, you get a equals to 1 and b equals to minus of 1, and we get to this equation. However, if you look into our original equation over here, it is s minus pi, and here we are having s plus of pi. So it is basically s minus of minus pi. Okay, so in that formula you have to bring it, and once you are here, you can apply the transformation, and if nothing is given, capital T is not given, you can safely assume that t equals to 1 second, and it will save you a lot of computation. And just you apply it into the equation, into this equation, and you will get the transfer function. Okay, similarly over here also, what you have, one transfer function has been given, you have t equals to 1 second. Okay, through partial fraction method you solve it, and after solving, you just what you call, apply the transformations, and after the application of transformation, you get the H-set method. Okay, same over here. Here if you see, capital T has been given. Okay, so capital T equal to 0.2 seconds. So one important thing over here, same thing, and when it is given and your capital T is less than this 1 second, then usually we multiply that what you call transfer function with capital T. It is for the basically for high sampling rates. Okay, so you put this capital T, put this thing, and you get the transformation matrix. Okay, and lastly over here we have this equation, same, apply partial transformation method. Okay, partial fraction method, then same thing, apply invariant method transformation in this equation, and you will be able to get the answer. However, when you are having this kind of equation, if you see over here, s plus 0.1 divided by s plus 0.1 whole square plus of 9, so it can be written in the form of s plus a divided by s plus a whole square plus b square. Okay, if you see, we have a direct transformation equation over there. You can just use this equation, put it over there, and you will get the results. Okay, so tomorrow I will start with the bilinear transform method, but now yesterday I saw you are not able to do even the simplest of this numericals. I would now ask you to solve these numericals yourselves over here and see whether you are able to do it, and if there are any these things, so we can try to resolve that. Okay, so please